This is the U.S. Navy's indoor ocean, which can simulate some of the world's worst weather conditions with waves that are only 4 feet tall. That's because the ships that are tested here are tiny. Scale models are valuable, because when testing a new hull design, they can highlight obvious issues pretty quickly. In this case, the issue is whoever came up with this design, and the solution is to replace that person. Since 1962, virtually all U.S. Navy ships and submarines have been tested here in this indoor ocean using scale models until 2007, when the water was drained from this basin, all 12 million gallons of it. But why the water inside U.S. Navy's indoor ocean is not salty, how test results from a scale model can be translated into a full-size ship, why these rails are curved, even though they look pretty straight, and why with all the advancements in computer modeling, the Navy still relies on old-school physical models, is not what you think. Hydrodynamic problems are very difficult to solve. Even with today's powerful computers, it is not possible to simulate the flow of water around a ship to the level of accuracy needed. And so, the best solution is to create a physical scale model of the ship and test it inside a giant water tank, a practice that goes back over a century. Officially called Maneuvering and Seakeeping Basin, or MASC for short, in 2007, this facility underwent major renovations. As part of the process, all the water had to be drained in order to remove the original pneumatic wave-making system from the basin. The upgrade took 6 years to complete, during which a brand new wave maker was put in place. This new system has 216 individually controlled electromechanical waveboards. They are like giant piano keys that move, but instead of sounds, they produce waves. This upgrade significantly enhanced the wave-making capabilities of the facility, allowing it to create virtually any type of wave, including ones that are so uniform, they don't even exist in the real world. But why would the U.S. Navy care about recreating the wave patterns that occur in the oceans around the world? Different oceans have different types of waves, with different frequencies and patterns. These differences stem from the geography of the region and the storms that occur in those areas. If a ship is going to be primarily operating in the northern Atlantic, it only makes sense that it would be tested against wave patterns that are prominent in that region. To do so, with the help of buoy and satellite data, the U.S. Navy is able to collect the wave energy spectrums of the oceans around the world, and can then replicate them here in this indoor ocean as needed. This way, what the scale models experience are the actual sea state conditions that a full-scale ship would experience in those waters, and one container ship had to learn this the hard way. New Year's Day of 2019 ended in disaster for container ship MSC Zoe. The ship lost 342 containers after being caught in a storm. In the aftermath of the incident, an investigation was ordered to determine the reasons behind this accident, and the Maritime Research Institute Netherlands, or MARIN, was tasked with simulating the incident. A scale model of the ship was built and waves similar to the ones in that area during the storms were simulated. The result suggested that the roll frequency of the ship and the frequency of the waves slamming against the hull would have resulted in roll resonance, causing heeling angles of up to 16 degrees. These strong rolls could have in turn applied large accelerations and forces to the containers, which could have exceeded safe design values. But another finding was that under-keel clearance between the ship and the seabed was less than 33 feet, and the up and down heaving had caused the ship to hit the bottom, sending shocks and vibrations throughout the ship and the containers on board. By the way, even though the actual ships would be operating in ocean saltwater, it is freshwater that the scale models are tested in. That's simply because maintaining the equipment is much easier, not having to deal with the corrosive effects of saltwater. Of course, saltwater is more dense than freshwater and therefore provides more buoyancy. But those differences in density are all mathematically accounted for when crunching the numbers. But something doesn't look right here. As you can see, the movements of these models in the water and their interactions with the waves don't look realistic at all. Full-size ships don't move up and down that quickly, and waves don't splash around that fast either. So how can these results from a scale model predict the behavior of the full-size ship? The thing is, if I sufficiently slow down the footage recorded from these models, suddenly things look a lot more realistic. This is not a coincidence. William Froude was a British engineer, naval architect, and a pioneer in testing model ships inside towing tanks. Through years of experimentation, he established a formula, now known as the Froude number, by which the results of small-scale tests could be used to predict the behavior of full-sized hulls. Let's say you have a model ship that is 50 times smaller than the real ship. According to the Froude formula, if we take the footage recorded from the scale model and slow it down by a factor of the square root of 50, which is about 7 times slower, the results would look identical to what the full-size ship would have experienced in those conditions. Mask provides the perfect environment to test the seaworthiness of model ships, but right around the corner, there's another critical test facility, the David Taylor Model Basin, which houses one of the largest towing tanks in the world. Simply put, a towing tank is a long pool of water where you drag a model ship through while precisely measuring the forces it takes to do so. The towing carriage, which is a movable platform, sits on 2 rails and can move from one end of the basin to the other. The model ship is attached in the middle of this moving platform. But the carriage also houses the sensors and computers that measure and record the data, as well as the scientists who are running the experiments. What they measure in these towing tanks is absolutely crucial to shipbuilders. A ship's hull shape directly impacts its speed. That's because different hulls experience different amounts of resistance as they move through water. The more the resistance, the more power is needed to move the ship at a particular speed. The question is, how much power does a ship need to operate at different speeds? The answer to that question can be found inside the towing tank. The calm water resistance test helps measure the resistance force. The model gets towed down the tank at several specified speeds, while sensitive sensors record the forces experienced on the model for each speed. This test is a critical one, because ship construction contracts include huge penalties if the ship doesn't make its specified speed. Imagine building a brand new aircraft carrier, just to find out it can't meet the required speed to safely launch aircraft. Towing tanks can measure the forces on the scale models with such precision that they can be translated into undisputed predictions for the performance of the full-size ship. But remember, precision is key. At the David Taylor Model Basin, the towing tank is located inside a climate-controlled facility. That's because even a small change in the water temperature could affect the readings. In fact, the experiments are so sensitive that the 1,886-foot-long carriage rails on the deep water basin were built to follow the curvature of the Earth. That's because the water from one end all the way to the other end naturally follows the curvature of the Earth. Back in the 1930s, constructing this facility was an engineering feat in and of itself. You may have seen these numbers on the side of a ship's hull. They show the draft, which is the distance from the waterline to the bottom of the hull. The more heavily a vessel is loaded, the deeper it sinks into the water, and the greater is its draft. What I found interesting is that during calm water resistance tests, the measurements are done at 2 different drafts. The first draft is the ship's design draft, where it will eventually operate when fully loaded with cargo and fuel. The second draft is the sea trial draft. When the ship is finally ready, it has to undergo sea trials. But during sea trials, ships are not fully loaded, and therefore will not be operating at their design draft. The idea behind performing the tests at 2 different drafts is that if the ship matches the speed predictions at the sea trial draft, when it's not loaded, then it should also match the predictions when operating fully loaded. Another important experiment is the self-propulsion test, where the model is tested while operating under its own power. But then, how come the carriage is still towing the model? The self-propulsion test initially begins by the ship model being towed by the carriage at a fixed speed. Remember, the carriage can record the drag force from the model as it's moving through the water. At some point, the propeller also starts rotating, until it eventually produces sufficient thrust to eliminate all the resistance force recorded by the towing carriage, at which point, the model is self-propelled. There are many other tests that measure different aspects of a ship's operation in the water, for example open water propeller test, which measures the efficiency losses of the propeller, the steamline tests which help visualize how the ship hull and water interact, water tunnel tests that allow for cavitation analysis, and even wind tunnel tests, because parts of the ship that's above the waterline create turbulence, and for aircraft carriers which launch and recover airplanes. Understanding the air turbulence is quite important for safe flight operations. It is the combination of all these experiments performed on scale models that gives designers and shipbuilders the confidence that once the full-scale ship hits the water for the first time, it can hopefully perform as expected.